So yeah. Yeah, that's just my bag, yeah. Yeah. Should I speak? Hello.
Okay, let's start.
They're just checking. Okay.
The second morning session with the last lecture by Alexander Ochirov. And I'm assuming that you are like me. We are now just so absolutely curious about how all this stuff can be applied to black holes. Please explain us.
Yes, so this is the last lecture. So before I get to black holes, I want to make a comment related to my last lecture where I had a nice question on higher points. And I said, oh, I didn't do anything. But actually, I did, I forgot. So yeah, yesterday we derived this formula. So this is the ordered amplitude 1, 2, 3, 4 with gluons plus and plus. We derived this formula for general spin. And way back when I was just learning this, the formalism, I derived this formula for QCD at endpoints. It's in that paper. It's like an analog of an MHV formula, but massive. So now it's endpoints. You have two fermions in here, and then you get n-2 plus helicity gluons. So, and it's natural that it's simple because now all of these formulae are huge matrices of amplitudes. For fermions, A and B are actual spins, spin projections of the fermion, of the Dirac fermion's spin. So of course you can set them to something, to 1 and 2, and actually this is a matrix 2 by 2. So this formula contains 4 helicity amplitudes. And in the massless limit, some of these helicities will go to minuses, and therefore there will be an MHV case occurring, coming from this formula. And the other ones will actually vanish because there's an m, there's actually a power of m. And now, so yeah, I did this for QCD, but actually it's trivial to extend it to general spin. So this will be now a general spin formula. It will be still all plus for gluons. So you can just guess what it is going to be, because all of the spin dependence here is just in this bracket. So I can just do this, raise it to the 2s power symmetrically. There's a factor of mass here, of course, that needs to account for the mass dimension of this factor. So since it's growing, I have to write 2s, and then I need to get an m here somehow for spin 1/2. So I have to write -2 here and erase this altogether. Right? So when s equals 1/2, it becomes just, yeah?
Sorry, in the massless limit, don't these all vanish?
No. In the massless limit, well, look at, Well, everything is incoming. So minus, plus, 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 minus. It's an MHV formula for a massless Dirac fermion. You can really check that it works. Oh, are you saying? Oh, yeah, that was another formula. Indeed, yeah, it should vanish, yeah. And actually, it did have this M, and it wasn't accounted for by anything else. Yeah, you're right. Sorry. Yeah, it vanishes in the massless limit because of the factor of M that was there. MHV. Yes, that's right. That's right. And yeah, actually in that paper I also have a formula for that case, and that's why I started confusing myself. But indeed, yeah, there's another formula. It has linearly growing number of terms instead of just one term. Here this term vanishes, but in a linearly growing expression that I'm not going to write here, in QCD, there's one term that survives the massless limit, and it becomes the MHV formula. Okay, thanks for correcting me. Yes, and so yeah, this is the answer at n points and any spin that one can write. And I think I even figured out a factor of, a consistency factor of integer part of spin. So, okay, good. The general spin formula is not in the literature, but it's a trivial generalization of what's in the literature. So let's get to classical black hole scattering now. And well, there's a lot of ground to cover. And so far I've been trying to be quite pedestrian and actually deriving most of things that I was going to, that I was talking about. And now I want to connect it to a lot of other different things. And let me use as a starting point some expression for Kerr for a linearized Kerr in linearized gravity, in which the metric is expanded around the Minkowski metric. So this is the graviton field. Kappa is the coupling constant. And Kerr, if Kerr is also linearized, its effective source can be written like this on the word line. So now we're talking about some word line on which there's, from very far away, you're looking at a spinning black hole. And, well, if it's a Schwarzschild black hole, I would just write a point particle without any spin structure. And Justin, at least in his paper, wrote 17, this formula, and I think it was written elsewhere beforehand. But he actually used it in his calculations to his benefit. So this is the word line delta function. So it depends on space-time, on the point in space-time, but somewhere along the z mu of tau path, there's a black hole going, and there's therefore a delta function kind of peak there for the source of Kerr. And well, one way to what I want to do now is then to couple it to my graviton. So a 3-point vertex would look like this: d4x h mu nu x t mu nu Kerr x. in Minkowski, in the mostly minus signature. Now, we want to look at scattering. So, sorry?
Can you explain the letter?
Oh, yeah, sorry. So everything, so these are momenta, of course. So a classical momentum is just mass times the unit for velocity vector, where unit for velocity vector is this, with tau as proper time. And a mu is rescaled by a mass, the spin of the black hole rescaled by its mass. It's very often used when talking about curved black holes, because now it has a dimension of distance, and it actually corresponds to, in the non-perturbative sense, it corresponds to a ring singularity that sources the black hole. So as opposed to the point singularity that sources a Schwarzschild black hole. Sorry? Oh yeah, and the star means if you take two vectors, you contract them with a Levi-Civita, a rho base sigma. Is there no halves? So A is a spin pseudo vector, and it's natural that I have to contract it with something parity odd in a sensible expression. So now I want to go to momentum space. And I'll use Donald's notation, where whenever there's a hat on some phase space, K, that means that it's just the phase space divided by 2 pi's. And when there's a hat on a delta function, that's just 2 pi. If it's an n-dimensional delta function, there are also factors of 2 pi implicit. So I want to take z mu of tau to be u mu tau. I want it to be to just go on a straight line from far infinity, and somehow interact with the gluon and go and continue its path. So here I will assume that k is small, so p1 and p2 are basically the same. So I will not distinguish between them now. And this T mu nu of Kerr in momentum space, it becomes delta function of p dot k, p mu exponent minus I k, the same indices, nu rho, p rho. And on top of that, we want to connect it to amplitudes. So we want to set the graviton on shell. So we replace it by its polarization tensor and delta function the on-shell delta function. Up to some creation and annihilation operators, that's what it should be on shell. And when you contract them, something happens. So on the support of these delta functions, well, the momenta, they are contracted now with the polarization vectors. So this is a tensor constructed out of two vectors that you would be using for photons, so I will just use them here. And this spin structure that occurs there, it can be rewritten as this interesting beast. So this is a non-trivial rewriting, and it relies more explicitly on an equation like this. So if you expand exponents to match this to that, you will see that you need something like this to hold. And yeah, to the power of j, if you expand it. As an exercise, I think it's an exercise number 7, you can just check that it works on in a frame where k has to be on shell and massless on shell. So let's just go to a frame where it looks like that. Then its polarization vector has to be space-like and transverse. So let's write it like that, up to assign the polarization vector should also be no, it shouldn't be space-like. The helicity polarization vectors are actually light-like, and this is a sensible way to write it. And finally, the momentum, it has to be perpendicular to k. So the energy and the z component must be the same for that to hold. But then it looks bad because I also want it to be massive, so I should be putting zeros here to actually have something even real, but then I would get a massless vector. So of course the actual support of these delta functions is complex, and you can take a frame where that happens. So it's some complex kinematics. This thing, and it must be complex, and it must be minus m squared. You can just check that it works, okay? So how is it related to anything that we've been doing so far? So now I remind you that the corresponding 3-point amplitudes that I want to be using look like that. I will now remove all factors of some minus, the minus factors that were only useful when I was talking about something that can connect directly to Feynman rules, but now I actually don't know proper Feynman rules for general spin. Or maybe some of them are known, but not all of them. And so this corresponds to that picture. Now P2 is outgoing, so I put a minus there. And it so happens that we could rewrite it in a very similar form to what you see there. You see that there's an exponent. Well, there was some kind of exponent already in position space. It became some other exponent with spin. And here we have some power depending on, well, at this point it's still an integer spin value. But you can check, and let me write it for spin half for the moment. So now I replace the classical spin tensor with spin generators. And let me, for definiteness, use the chiral fermions. And therefore, I'm using sigma mu nus that were all over the place before. And just by opening the definition of these so there will be I over 4 sigma nu bar minus sigma nu sigma mu bar. So when you contract it with k, you just get k massless spinners. And when you contract it with the polarization vector, I took minus helicity for definiteness, you will get qk. And for the other combination, you will get this. And this came from the denominator of the polarization vector definition. You can see that there is a cancellation of the reference vector dependence. And moreover, you see that this exponent, if you now, so this exponent becomes just k mx minus 1. So if you expand this exponent, you will have to write 1 plus this plus the same thing squared. But k, when you act with k on k, you will get a spinor product of k with itself, which is 0 by antisymmetry. So in this representation, which is just spin 1 half, you will only get 2 terms out of the exponent. And these terms are just these terms, plus 2ak k1 mx. That's it. And now it's up to a minus sign is just the other bracket. So we took a minus helicity, and actually we know that minus helicities here are written in terms of these brackets anyway for minimal coupling. Minus 2. So this was spin 1 half. I rewrote the square bracket in an exponential form. Going to the tensor product case for general spin, I can rewrite, actually, yeah, I wanted to flip them, but just for future. So this I can rewrite as an exponent minus, so I generalize this, and you can check that it works. And now the sigma mu nu is a tensor product version of the spin half sigma mu nus. And similarly, 2s equals that. Bar plus now, plus 1. So we see that there is a way to extract some exponential dependence on spin out of our minimal coupling amplitudes that match nicely to the exponent in the classical Kerr source. So this is how, this is not rigorous, and at least it wasn't rigorous at that point, but this match, this was the first match to Kerr from this on-shell perspective. So this is me with Justin and Alfredo. And at the same time, our colleagues in Asia were doing a match using Wilson coefficients on a world line. And I don't want to get into that in any way. But from a different perspective, from the effective field theory perspective, they could also see that there is a match happening. Good. Something else that, okay, again, now I will be emitting minus ones of this form and of this form, not because I haven't done calculations with them, but they really don't do any good anymore if you don't want to match any Feynman rules. It's just that Feynman rules tend to have well-defined connections in QFT, conventions in QFT, and this stuff I don't think we need to follow them. Great. So another way to rewrite this exponent is a very chiral way, actually. Well, this was quite chiral as well, but just because there is a factor of polarization vector sitting in the denominator doesn't mean that it has to be there. It always comes with another polarization vector upstairs. So in fact, you can get rid of it and rewrite it in this way. And now here, A's, well, they are rescaled Pauli-Lubanskis. They are 1 over m squared, yes, mu nu rho sigma, sigma nu rho p sigma. And, well, let me write it here. then rho sigma. In these formulae, I understand them in the tensor product sense, so actually they have lots of indices, alpha 1, alpha 2s, beta 1, beta 2s, and I think I was defining these guys yesterday. And originally we were using the exponents in this form, but I want to actually use exponents in this form, which are more convenient. So I'm going to raise this board, and you'll have time for questions. Yes?
I think I'm starting a little bit with the bigger picture here. So what was your line? What was your goal with this? So you understand the math, yeah, result, graphical pattern, tensor of the tensor.
So we want to use amplitudes as for classical physics. And amplitudes, and the thing about amplitudes that helps us as opposed to the people doing classical perturbation theory, is that they have to do it in a gauge-invariant way usually, gauge-dependent way, and our building blocks are always gauge-invariant. And well, the group in California, as we Byrne and other people at UCLA and Caltech, they have already been doing this for spinless particles, for spinless black holes, and they were producing new results, and at lower orders they were reproducing known results in classical theory. So there's a clear understanding that in the spinless case, a massive scalar coupled to gravity reproduces classical results for Schwarzschild black holes. Now, we here do amplitudes that contain scalars as this trivial case, and they depend on an integer spin value, on spin, and they depend on it through some quantum through a quantum way, which is very different from how very different from the momentum. Momentum is something continuous, and so if you want to translate it to a for velocity, you just put a factor of mass, right? And basically, a quantum momentum can be easily translated into classical momentum from the on-shell perspective. But our starting point here has spin in a very quantum way, implemented in a very quantum way, and we want to extract the spin dependence that would correspond to classical spin. And I was showing how one lecture ago I was showing how spin expectation values of the Pauli-Lebansky operator can be mapped to spin quantized along some direction, and of course it's implicitly quantized in powers of Planck's constant, which in the classical limit goes to 0. So clearly we want the integer spin s to go to infinity to extract some finite spin in the classical limit. And so that's one thing, but also we want to extract a dependence on, indeed, a spin tensor or Polobansky spin vector, and rewriting things using operators allows us to do it. It's not rigorous. The full some of the things that I will be doing now will not be rigorous, but they're going to become more rigorous within a year, for sure. So, so the point of this is to do calculations that certainly apply for the spinless case and contain some spin dependence that we massage into a way that can then be interpreted classically. Okay? Yeah, thanks a lot for the question. So indeed, let's now feed it into scattering situation. And in a scattering situation, I will be using results from other people. So I want to consider two black holes, tree-level lowest order scattering. PA comes in, PB comes in as well, and PA plus delta PA comes out, and PB minus delta PA comes out by conservation. And this is one of the observables that one can define in quantum field theory, and then take the classical limit. And there's a formula for it. Let me write it first. K mu and now this amplitude here, it corresponds to kinematics that I will be drawing using a slightly different rules. So now I will be saying that this is P1, P2, P3, and P4. And I made it only explicit, explicit its dependence on K, on the exchange momentum. And so this formula comes from quite rigorous considerations in quantum field theory. And I haven't written all of it. There is a way to make it shorter, which is to use these brackets. And these brackets, and this is only a tree level. There is another contribution that comes in at higher orders. So this transition here corresponds to the following rescaling. From the analysis, they realized that massless gauge bosons must have momenta that scale with h, and something classically sensible is a wave number. So as momenta in Q of t, they go to 0. At the same time, P1 and P2, P2 is just P1 plus K. They go together to something that we will be associating with this PA. And at the same time, I will just be using this as an average, A meaning average, which I'm allowed to do. And this PA will really be classical. It will be the black hole's mass times its 4 velocity. So, by the way, sorry about using A and B now to label black holes, but actually I will be omitting little group indices now, so there won't be too many A's. Oh, there's an A, of course, for the spin, but that has an index, a Lorentz index. At the same time, these momenta go to PB, and I will be associating it with also an average. But this subtlety is very quite irrelevant at the lowest order. So this is what happens implicitly in these brackets that perform some rigorous analysis of wave packets that peaked around some classical values. And also reinstated powers of H bar. And a similar formula, now we're considering the spinning case. So there's a similar formula for the spin kick or the angular impulse, depending on your aesthetic linguistic preferences. So it contains a similar Fourier transform with delta function, so it's effectively a two-dimensional Fourier transform, and then contains this, and they derived it so that has been derived half a year later. Now, yes? Yes. So we're looking at an exchange momentum that is small, classically small. And that's, you can, for the moment, let's consider it as a result of analysis by Cassara, maybe, and O'Connell. And that corresponds nicely to what I've been doing upstairs, actually.
Yeah, but what is the meaning of the wave number, or why do you need it?
It's just, I'm saying that this wave number, that's something more classically sensible.
Yeah, but the whole thing goes to 0.
Yes. Yeah, the whole thing goes to 0. But H bar goes to 0, and K bar stays finite. Whereas in the same limit where H bar goes to 0, these momenta contain a classical mass, so they don't have to go to 0 in any way. So the classical mass actually prevents these momenta, leaves them sensibly classical. Great. So something that has happened here was also that this spin operator is just rescaled spin operator here. It acts. There's a commutator with the amplitude. So what does this mean? That's something new. That's the spin operator understood as an expectation value. So I've done quite a lot on that part. One lecture ago, I defined this expectation value. Well, now, and I actually had a formula for it. Yeah, let me do it. Let me call all of these B's and all of these A's. So, okay, when I was quantizing spin, I was using I was using the expectation value where I was setting b's equal to a's, but I also gave and derived a formula for a matrix element of A and B with different A and B's. So this looks like a one particle element of the spin operator with the spin states. And now the physical spin states, they're defined by, they're characterized by their little group indices. And of course, in that space, there's an operator acting. This is an operator acting on the physical spin indices. And an amplitude is also a matrix converting spin indices of particle 1 into spin indices of particle 2, and vice versa for the other guy. And this operator, the spin acts as an operator on those indices, now completely physical. And these physical indices, of course, they correspond to the little group. Well, let me still write it here. So little group, which is SU2. Now, at the same time, it's SO3 in rest frame up to the double cover issue. And there is an algebra that they have to obey. So the way to write this algebra covariantly is to write it with a Levi-Civita four-dimensional Levi-Civita tensor, mu nu rho sigma p rho. Yeah, so A sigma. You can easily see that in the rest frame, this is PA. In the rest frame, it boils down to SI as J equals I Levi-Civita SK. Well, that lets us actually massage this into something into I over m squared mu nu rho sigma pa nu sa rho no a yeah and then a partial derivative over spin. So, I mean, we want to do things classically, so we want to look at this amplitude and read off its dependence on spin as a function. So once it's a function depending on spin, you can at least naively take a derivative, and then this operation will act through this commutator and do this. It's a naive thing because actually spin should be transverse, and so it's a constrained operation, but let me just do it like that. And similarly, K nu is minus, no, is it? No, it's just plus I derivative or by B nu, just because you can gain it from this exponent. So this lets me, in a not entirely rigorous way, rewrite it in the following form. Where do I have it? Minus derivative b mu, something happening to the 4-point amplitude is a 1 over I. It's just a convention thing. A mu, I will write it as minus Levi-Civita over I m. Maybe let's take a break now.